6 monitors, 10 computers, 240 Intel i9-15900KS cores powered by the sheer and divine willpower of the sun. This is parallel computing.
And welcome to the future.
According to Moore's law, the number of transistors on a CPU chip roughly doubles every 2 years, boosting computational power. For decades, this observation seemingly held true, allowing us to build complex machines and explore the far ends of space. However, in recent years, we have begun to hit a breaking point, as chips are starting to approach their physical limits. As a result, continued advances in computing are unfortunately no longer guaranteed. So what is the solution? Well, if we can't improve the chips individually, then why not just use multiple of them at the same time?
So parallel computing is the idea of breaking up a task into smaller tasks, and each task is computed with a separate computing resource, like processor or the GPU. For those who took BO9, you can kind of think of it like a child process that's created with the parent process, which still runs parallel to the parent process. Compared to serial computing, parallel computing is oftentimes faster when dealing with larger input size, and that's because of the extra computing resources that are used at the same time, as compared to just one when you're doing serial computing.
One of the ways this technology can be used is to make algorithms execute faster. Let's take a look at a few examples.
Let's start with matrix multiplication in C with parallel computing. For this, we'll use OpenMP, which is a popular parallel programming API for C, C++, and Fortran. We'll be using this to demonstrate application of parallel programming languages. Let's look at this tester I have open right here. We're going to run the matrix multiplication serially and parallelly and just see how they compare. So let's do that real quick. These are matrices at 1024 by 1024, so they will take a long time because matrix multiplication has a complexity of O(n cubed. So let's see what happens when I finish running this. Alright, serial multiplication took 6.9 seconds while parallel did not even take a second. So you might be thinking this is like a one-time thing, right? But no. Actually, if you run it 100 times, you see that this trend still persists, so what's going on? Let's have a look at serial matrix multiplication. You realize that this is the normal implementation for any matrix multiplication out there, and parallel actually does not look any different. So the reason for this is because even if parallel program relies on thread management, OpenMP abstracts away a lot of the details on what's actually happening to those threads. The API that manages those threads is called pthreads, and OpenMP does indeed use it. We will look into how OpenMP and the GCC compiler does that a little bit better later. Alright, let's switch to Haskell. This code looks rather familiar because we did this in our lab 6, but we're going to do some parallel computing as well. Let's start with the type definition. So we have this NF data thing here that basically says that A should be able to be evaluated to the way we want it before passing it into the parallel computation. So if you want more information, just check out the docs. So here we're doing the transpose computation outside of the map, which is because we don't want each thread to compute the transpose once and have it use that instead. So now we have our parmap and our rdeepsec. What are those? So parmap is basically just map, but it takes in an extra function that basically says what you want to do with the elements in here. Rdeepsec basically says you want all the elements in here to be fully evaluated before passing it into each thread, which helps with preventing errors when doing the parallel computation. And let's give it a run because I have it loaded and ready. This will take a while because these matrices are 500 by 500, so I'll catch you guys later. Okay, welcome back. Parallel beats serial again, but there's more to it because this is functional programming. So we learned something called referential transparency, which means that functions don't depend on the global state of the program, just the variables that was passed into it. This implies that there are no side effects as a result of any function call in functional programming. Since there are no side effects, there will also be no race conditions since no two processes are modifying the same thing and therefore does not depend on each other for their own computations. This is one of the reasons why functional programming is really good for parallel programming.
As we saw from the previous examples, parallel programming relies on splitting tasks into multiple subtasks that execute simultaneously. But how exactly do compilers handle this? Let's take a look at how the GNU GCC compiler and the OpenMP API that we saw earlier do all this magic. Keep in mind that other compilers that support OpenMP will typically work in a similar way. Now, before we jump into it, it's important to note that OpenMP uses a shared memory model. What this basically means is that all threads or processes use the same shared memory. That is, global variables or any variables that are outside the parallelized code block are shared between all processes. This has some benefits, like how threads can read and write from the same variables, but it also introduces some downsides, such as race conditions when multiple threads try to access or modify that same variable, and some synchronization issues. We will get into that a bit more later. For now, notice how function programming paradigms might be pretty handy here. Pure functions, no side effects, no race conditions. Seems pretty good, as we discussed in the previous part. And now, let us look at some simple parallel programs and see how the magic really happens. The code you see here is a simple parallel version of the classic Hello World program. I'll run it and I'll show the output, but before I do so, I want to go over what this little pragma thing is, and what the compiler does with it. Now syntactically, it looks a lot like a preprocessor directive, and it kinda is, but what's interesting about it is that it's not actually handled by the preprocessor. Instead, it is simply passed onto the compiler, which then interprets it as a hint, basically saying something like, hey, parallelize this block of code. So basically, during the semantic analysis phase, when the compiler encounters the directive, it recognizes this parallel region and outlines it, meaning that it encapsulates this body into a separate function that can be run by multiple threads. This all happens in the step of generating the intermediate representation of the code. Then, within that intermediate representation, the compiler inserts calls to the OpenMP runtime functions, which later handle the actual creation and management of threads, which themselves then rely on the operating system to actually schedule and run those threads on actual physical cores. So now we can compile and then run the program, and we can see that we have multiple instances of this print statement. Each of these was simply part of a thread that contained the parallelized code block, which simply only contained the print statement in this case. I got 12 of these threads, and the reason for that is basically just because OpenMP by default creates a number of threads based on the number of logical processors that you have. I have 12, so it made 12, but we can change that by setting up an environmental variable. Now looking at the loop, we can modify the directive to include this for, and what this basically does is now each iteration of the loop gets assigned to a specific thread. So for example, if we compile and run, we can see that each one of the iterations has a specific thread tied to it. Notice how they're not necessarily ordered in terms of the iteration. They're just basically because whichever iteration finishes executing first or spits out the standard output is the one that's we're gonna be seeing first at the standard output. Also note that depending on the number of threads that your system can make, some of the iterations of the loop could be assigned to the same thread, which are then executed sequentially. So for example, since I have 12 logical processors, if I do 15 and then compile and run the program, we can see that some of the threads contain multiple different iterations of the loop. And finally, one of the ways that we can mitigate some of the issues that we talked about regarding race conditions and so, is to use the following preprocessor directive, which basically tells OpenMP to only allow one thread at a time to enter this so-called critical block.